Hello, calculus students. This lecture video is about moments and centers of mass. So the first case we will look at is where we have a finite number of points, n points, and we are working only in one dimension. So we suppose that several point masses that we'll label P1 through Pn are located on a number line. So here's our number line, right? And we have several points, and each of those has a mass. So if this is P1, then we say that the x value where that's at is x1, and the point has mass m1. So each point has a position and a mass. We define the moment of a point mass with respect to the origin to be mi times xi. So if we imagine this is 0 and this is the point pi, it's at location xi and it has mass mi. We take the distance from the origin, the directed distance in case x is over here on the left side, and we multiply by the mass. So this represents the tendency of the number line to rotate about the origin under the influence of that point. So just to simplify, if this is 0, we can imagine this as the fulcrum of a seesaw or something like that. And so if we have this point, pi, then this is going to tend to make the number line kind of tilt this direction about the origin. We define the moment of the system, so meaning all the points together, to be the sum of the moments of the individual point masses. So capital M we're using for moment. We add up all those individual moments, and then that's the same thing using sigma notation. We define the moment of the system to be the sum of the moments of the individual point masses. So we use capital M for the moment. This is the sum of those n moments, and this is the same sum, just using sigma notation. And then we understand that the total mass of the system is you just add up the individual masses. So here's an example. Point masses are located on the x-axis as shown in this figure. We want to find the moment and the mass of the system. So finding the mass is a little bit easier, so we'll do that one first. And to find the total mass, we just add up the masses of these 4 points. So 11 and 7 and 9 and 4, and that is 21. So the mass of the system is 21. To find the moment, we add up the moments of each of those 4 masses. To find the moment of each point, we take the mass and we multiply by the corresponding x value. So this first point has a moment 11 times -4. The second point has a moment of 7 times 2. The third point has a moment of 9 times 7, right? This x value is 7. And the last one has a moment of 4 times 12. So -44 and 14 and 63 and 48. And that gives us an overall moment of 81. I just want to remind you notation-wise, lowercase m is mass and capital M is the moment. Next, the center of mass of a system is the point at which the system of point masses would balance. So the center of mass of the points is given by the moment divided by the mass. So the total moment of the system divided by the total mass of the system. We use the notation x bar to be the center of mass. So in our general situation, if we have these points, the question is, where does this fulcrum need to be where this teeter-totter would balance? Okay, so now we will find the center of mass of the system that we looked at in example 1. Remember, we found that the moment is 81, and we found that the total mass is 30. So the center of mass is the moment divided by the mass, or 81 divided by 30, which boils down to 27 tenths or 2.7. As far as understanding, that means that this number line, if we put a fulcrum at 2.7, the number line would balance right here on the fulcrum. The moment, the tendency to rotate the tendency to rotate counterclockwise based off these 2 points would be the same as the tendency to rotate clockwise based off those 2 points. Now we'll move on to case 2, where we have a finite number of points, but we are in 2 dimensions. So now suppose we have our particles, but instead of on a number line, they're in the plane. Okay, and each point has a location in the plane and a mass. So here's a point mass, P1. It has a location, x1, y1, and it has a mass, m1. Then we define the moment of the system about the y-axis. So the tendency of these points to cause the system to rotate about the y-axis is what we're thinking for my. We define the moment of the system about the y-axis in exactly the same way as we defined the moment of the one-dimensional system about the origin. We take each mass and multiply by its corresponding x value. We add all those together. Similarly, we define the moment of the system about the x-axis, just thinking about the vertical distance from the origin. So we take the mass and multiply by the corresponding y value for each point and add all those together. So here is an example. Find the moments in the center of mass of the system of objects that have masses 4, 6, and 8 at points 4, 7, -1, 6, and 9, 0. So just for understanding, we have 4 points. One is located at 4, 7. That one has mass 4. One is located at -1, -6, and that point has mass 6. And the last one is located at 9, 0, and that one has mass 8. So we will find the moment about the y-axis. So that's the tendency of these points to cause our entire system to spin about the y-axis. Because we're thinking about spinning about the y-axis, it's the x-coordinate of each point that matters, right? How far away that point is from the y-axis. So our first point, this top one, has mass 4 and is at x value 4. The second point down here has mass 6 and is at x value -1. The third point has mass 8 and is at x value 9. And so the moment about the y-axis is 74 altogether. When we find the moment about the x-axis, we care about the vertical distance of each point from the x-axis. So this is measuring the tendency of our system to rotate about the x-axis. So our first point up here has mass 4 and is at y value 7. Our second point here has mass 6 and is at y value -6. Our third point has mass 8, but its y value is 0. This point on the x-axis won't cause any rotation about the x-axis. So overall, our moment about the x-axis is -8. Finally, to find the center of mass, we're looking for the point x bar, y bar, where if the entire mass was located at that one point, the moments would be the same. So we find x bar by dividing the moment about the y-axis by the total mass. So I guess we need to find the total mass. So the total mass is 4 plus 6 plus 8, just adding up the masses of the individual points. So that's 18. So x bar is 74 divided by 18, which is 37/9, or just to make it easier to understand, 4 1/9. And y bar is the moment about the x-axis divided by the total mass, which is -8 divided by 18, or -4/9. So the center of mass is 37/9, comma, -4/9. As far as understanding, that's x value 4 1/9 and y value a little bit less than 0, so about here. So if we took the entire mass of 18 and concentrated it right there, the moment about the y-axis and the moment about the x-axis would be 74 and -8.